Hello everyone, my name is Roberto
And I'm Petar.
and we'd like to give you a glance at what we've done this summer.
But let us start from the beginning. As we all know, every computer uses some kind of memory to load from and store data to it. Fastest memory available to CPU is its own registers, which can be directly accessed without any waiting. But their number and size are very limited. Next are CPU caches, which can be further divided into different levels depending on their size and speed. Although bigger, caches are still not spacious enough to hold all data needed for everyday programs, and are only used as mediators between processors and our next kind of memory, DRAM. DRAM, or Dynamic Random Access Memory, is used as main memory because it's large enough to contain all the data and reasonably fast enough to provide that data to computers. All mentioned storage types so far miss one important feature: persistency. And for that we need to use much slower devices like SSDs and old-fashioned HDDs. Although SSDs give big improvement over traditional disks, they are still way slower than main memory. We are maybe at the beginning of new era of persisting data, because there is a new type of memory called persistent memory, which gives us both speed comparable to DRAM and persistency like disks.
This memory not only has powerful qualities mentioned before, but also can be used in various modes depending on the use case. First, the device can be used in memory mode, which turns RAM into a last level cache and uses persistent memory as volatile memory. This way, computer immediately gains transparent increase of main memory and introduces page swapping for large memory programs. The second mode is called UpDirect and it exploits device persistence feature. Memory can be used to permanently store data and it's much faster than using regular disk, even SSDs. Storage becomes persistent, but the way of accessing it is also what can be manipulated. FSDAX, or File System Direct Access, gives a standardized way of using persistent memory, which acts like regular disk mounted to the computer and can be used like any other device. Memory can also be accessed directly via Persistent Memory Developer Kit, which fully exposes device hardware to a programmer and gives an opportunity to customize application for most performance. It's time now to talk about the other half of the story, CHARM++.
CHARM++ is a C++ parallel programming framework which abstracts all parts that can be parallelized into char objects. Each char holds its own state and communicates with others by invoking their so-called entry methods, which can be looked as asynchronous message exchange. Interesting feature of CHARM is its system for fault tolerance, which works by checkpointing an application in some moment of execution. That checkpoint can be used later to roll back to previous consistent state if any error or failure occurs. Project goal was to greatly reduce checkpointing time by using new persistent memory technology, and with that introduce method-level transactionality if possible.
Here is the plan we followed to introduce PMEM into the CHARM++ checkpointing framework. First of all, we analyzed the code already present in CHARM++, since the best way to integrate our approach is to realize it in a similar way. After the analysis part comes the implementation part, in which we create our checkpointing mechanism based on PMEM. Finally, the last step tries to evaluate the functionality of the modules introduced, mainly in terms of performance.
For checkpointing evaluation, we've used a built-in stencil application that uses Jacobi method to determine the solution of strictly diagonal dominant system of linear equations. Each test configuration depends on two factors: number of chars which handle portions of input arrays, and number of processors and nodes that are available to application. As we can see, persistent memory usage shows a huge speed up over regular disk, and it's quite close to the performance of DRAM. Both FSDAX and PMDK approaches give expected gains and are close to each other in terms of performance. Worth mentioning is that although the existing disk caching method that uses main memory as I/O mediator gives solid improvement over the method that directly operates with disk, it is still behind our new persistent memory.
From those tests we can take out some meaningful conclusions. The first one is that performance of PMDK and FSDAX is very good and similar. The last point is due to the dimension of checkpoint, big enough to ensure efficiency. The other conclusions are that disk cannot achieve the same result. Either it obtains performance at the cost of consistency, via caching, or vice versa, via direct operations.
All the performance obtained with checkpointing via persistent memory can be used to introduce new functionalities into the framework. As we mentioned, transactional checkpointing is one of those. It is based on the ACID properties, a set of constraints that limit the effect of failure to a single char. The main point of transactional checkpointing can be summarized in a single phrase: either all messages are sent or none. Usually, this approach is not used outside of the database field due to its poor performance induced by constraints, but may become viable by exploiting speedup obtained with persistent memory.
It also requires the system of checkpointing to be asynchronous, which can be difficult to achieve because it's not directly supported by Charm++. And this is definitely one of the ways to develop this project further. Thank you for your attention.